a great pleasure to introduce Markus Werner for today's lecture. He's a part of DKU and the Math Center. Well, Markus did his PhD and his master degree in Cambridge in the United Kingdom. And then he spent some time in Japan, in Kyoto and Tokyo as researcher and assistant professor. And he joined Kunshan University roughly 1 year ago, I guess, Markus, right? More or less.
Oh, in July. So actually,
in July.
Just a few months.
Okay.
Yes.
Just a few months. Okay.
Yeah.
Okay. And he's an expert on geometry. And today he's going to give a very interesting presentation, as far as I see, which is related to geometry and physics. So his topic of today's talk is gravity and light, the mathematics of gravitational lensing. And please, Markus, you have 1 hour time and more or less 30 minutes for questions.
Okay, thank you very much, Peter, for the introduction. So let me share my screen. So this is from an iPad. Hopefully this works. Okay. So can you see this?
Yes, very good.
Yeah.
Okay, great. So let's start. So again, thanks for coming. And my topic today is related to a subject at the interface of mathematics and astronomy, right? And as Peter was saying, I'm a new member of DKU. So I'm particularly delighted, really, that our center is named after Zhu Zhongji, a scholar from Chinese antiquity who was both a mathematician and an astronomer. And of course, in the old days, this kind of connection was quite common. Right. Another example that I'm familiar with from Cambridge would be the ancient Lowndean Professorship of Astronomy and Geometry, which still exists. But of course, nowadays, this connection is less common. However, in this talk, I hopefully want to convince you that the connection is actually still there. And in fact, it thrives in subjects like general relativity and the mathematical properties of gravitational lensing. Even to the point that sometimes astronomy can help mathematics, believe it or not. So I'll give you one example of this later in the talk. So we're talking about gravitational lensing. Let's start with some pictures. So on the right, you can see a typical gravitational lens system. And this is called the Cheshire Cat lens, because it looks a little bit like this smiley cat from Alice in Wonderland, right? And well, the eyes of the cat, so these orangey blobs here are actually massive galaxies whose mass causes curvature of space-time, such that the light from galaxies behind it is deflected and sometimes even split up into several images. So we can see this up here on the right. So these things are actually images of the same galaxy gravitationally lensed. And again, later we will see how gravity can actually give rise to multiple images of the same object. Now, on the right, you can see a recent and very famous picture, which is, well, the shadow of a black hole in the center of the galaxy M87. And this was taken by the so-called Event Horizon Telescope. Now, actually, what we can see here isn't really the event horizon of a black hole, even though this is as close as we've ever been to imaging a black hole. But what we can see there is the so-called photon region or photon sphere of the black hole. And again, later in the talk, I will give a different geometrical interpretation of what a photon sphere is. So mathematically, gravitational lensing can be studied in various ways. In astronomy, people use what's called the standard approximation or thin lens approximation, which is physically an approximation. However, it's tremendously useful, and it's actually mathematically interesting in its own right. So I will discuss how this theory gives us constraints about the number of lensed images that we can get using Morse theory and also complex analysis. And then I will talk about the connection between the magnification of lensed images and Lefschetz fixed point theory. But gravitational lensing, of course, really happens in space-time. So then I'll talk about a different approach, which is called optical geometry. So this is spatial formalism, but it uses proper differential geometry. And it turns out for static spacetimes, the corresponding optical geometry is Riemannian. And I will introduce a method based on the Gauss-Bonnet theorem, which can help us to understand how many lensed images we can have and also how strong the deflection is. And then this framework will also be used to discuss the isoperimetric problem in Riemannian optical geometry. So this is then what provides the connection with photon spheres that I've just. Then moving on from static spacetimes to stationary spacetimes, it turns out the corresponding optical geometry is actually a Finsler geometry of Randers type, and I'll say more about this later. And I just described briefly how we can extend this Gauss-Bonnet method to Finslerian spacetimes. Finslerian optical geometries corresponding to spacetimes of, for example, rotating black holes like the Kerr solution. So all of this is within the framework of general relativity, of Einstein's theory of gravity. And at the moment, of course, there's so much observational information coming in that many people are interested in modifying the theory of gravity. So we can also ask, well, how to go beyond Einstein's theory. And there are various approaches. I'm particularly attracted by a new approach, which is called constructive gravity. And the idea there is that rather than just stipulating some modification of the Einstein theory, we would like to derive gravity theories such that they have a well-posed Cauchy problem by construction, hence the name constructive gravity. And I think this is very promising because it actually allows us to study even non-metric backgrounds. So one can look at something called an area metric, and then this will give rise to qualitatively different optical effects, for example, birefringence and things like this. So time permitting, at the end, I'll mention something about this as well. Okay, so let's start then with gravitational lensing in the standard approximation, very simply. So this is the basic picture. So let's say you have a Euclidean three-dimensional space. So if you want to take into account cosmology, it's conformally Euclidean. And in that space, we have two parallel planes. One plane is called the lens plane. This contains the gravitating object, the gravitational lens. And the other plane, which is behind that, as seen from the observer, is called source plane. That contains the light source. Well, and then light rays are, of course, straight lines, except where they intersect the lens plane, and then they get a little kink or an impulse. And this is why we also call it an impulse approximation. So of course, physically, this is not really what's going on, but it's a very close approximation given, astronomical scales. So it's actually very useful. Now, an actual lensing model is then implemented by projecting the mass into the lens plane and then basically solving Poisson's equation. And then this gives rise to what's deflection potential psi. Now we can imagine light traveling from the light source up here to the observer via some point x in the lens plane. Then the total travel time or the total time delay is given by what's called the Fermat potential. So it's this function here defined on the lens plane, where y is the fixed, say, coordinate of the light source. And the Fermat potential consists of two parts. So first of all, it has a geometrical part, which is simply, due to the configuration of these piecewise straight light rays. And then there's a gravitational part, which is again this deflection potential. And that's the gravitational time delay, or Shapiro effect, as it's also called. Okay. So now Fermat's principle tells us then that out of all these possible parts, the actual light rays are those for which the Fermat potential, the travel time, is stationary. So using this condition then, we can derive what's called the lens equation. So here's the lens equation, and it maps points at x in the lens plane back to points y in the source plane. Or another way of saying this is there's a lensing map, we call it eta, from the lens plane to the source plane, so that physically, physical gravitational lens images seen in the lens plane mathematically are really pre-images of the source position y under the lensing map. Right? Or yet another way of putting this is a gravitational lens image is a critical point of the Fermat potential. So now we can ask a basic question. Given the setup, how many lensed images can be produced, right? So this will depend on how many critical points of the Fermat potential we have. And of course, the Fermat potential is just a function of two variables. So we know, of course, what type of critical points can occur. And these are minima, saddle points, and maxima, which we can classify then according to the Morse index, running from Morse index 0 for a minimum, to 1 for a saddle point, to 2 for a maximum, right? And then we can use Morse theory to count the number of critical points. And there's a classical theorem by Morse, which then says, well, if you have a closed manifold, then the alternating sum of the number of critical points of Morse index lambda adds up to the Euler characteristic of that manifold. So how can we apply this theorem in our gravitational lensing situation? Well, first of all, to keep things simple, let's suppose we have an isolated lens. And actually, that's a fairly good approximation, because a lens would be a galaxy, right? And the galaxy is just sitting somewhere in space, and actually space is fairly empty. So this is a pretty good approximation in most cases. So then let's also have some kind of regularity conditions such that the deflection potential is smooth. And by virtue of the lens being isolated, we can actually also say that the deflection potential must diverge only logarithmically as you go away from the lens. And the reason for this is that, remember, we're solving Poisson's equation. So it's basically a delta function. So you get a Green's function, right? And in 2 dimensions, of course, this is basically a logarithm. But the Fermat potential has 2 contributions, right? The geometrical part and the gravitational part. And the geometrical part is polynomial in X, essentially. So this will always dominate the logarithm. So as we go away from the lens, the deflection, the Fermat potential will actually diverge like a paraboloid. So therefore, for an isolated lens, we get a picture something like this. So a lens is located somewhere in the lens plane. And if it's isolated, we're now assured that all the lensed images, which will be critical points of the time delay, let's say here, will be quite close to the lens. And as you go away from the lens, the time delay will just go up like a paraboloid, like this. So in other words, lensed images will have compact support, and well, we still can't apply we still can't apply Morse's theorem, because that's for closed manifold. But what we can do now, artificially, close it. We can cut the surface at a sufficiently large value of the Fermat potential, and then give it a cap like this to turn it into a topological sphere. Now, of course, doing this will introduce additional critical points, right? So, for example, a maximum here at the top, which won't be a gravitationally lensed image. So we have to take this into account when actually doing the counting. But now we can apply the theorem, and so we get the following. So from Morse's theorem, we can say that the number of minima, right, this was -1 to the Morse index 0, so it gives us a plus, number of minima minus the number of saddle points, -1 to the 1, plus the number of maxima, -1 to the 2, plus this additional maximum at the top that we've introduced, equals the Euler characteristic of this closed surface, which is a topological sphere. So that's equal to 2. Now, on the other hand, the total number of lensed images is, of course, just, well, the sum of minima, saddle points, and maxima. So now you can see, subtracting these 2 equations, we can actually deduce that the total number of lensed images is 2 times the number of saddle points plus 1. So in other words, it's an odd number. And so that's one way of understanding a classical result in this area called the odd number theorem in gravitational lensing. So this was discovered by Berg in '81. And actually one of my collaborators who worked at Duke for a long time, Ali Pesses, was one of the pioneers of this subject. So in the 90s, he generalized this result to, well, to much more general situations. Well, I won't go into these cases, they're a little bit more technical. And actually, you don't need to use this standard approximation. There's even a space-time version. So one could work directly on the space of geodesics and also derive the odd number theorem. Well, and the nice thing is it actually works in practice, right? So here's another real picture. So you can see a sort of, well, orangey blob, let's say here. This is the center of a, well, I think of a galaxy cluster, really. This provides that causes these multiple images to occur. So we have 3 images of a lensed galaxy, here, here, and here, right? And 5 images of a quasar behind the lens. So here, 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 and here, and here. So again, the odd number theorem is actually satisfied. Now, can we say more? So are there any bounds on the number of images? So let's consider a simple case again. So let's say in the lens plane, we consider n point masses. So these can have different positive masses, and we can arrange them in the lens plane as we like. And physically, you can think of this as just a bunch of stars, for example, or a bunch of black holes. At this level of approximation, it doesn't actually make much difference. So we have n coplanar point lenses, and the question is, well, how many gravitationally lensed images can such a configuration produce at maximum? So we're free to rearrange them and also change the position of the light source. What's the maximum number of lensed images? And well, you might think it's fairly simple. This is surely an undergraduate research problem, but actually it's not. So let's see what was known in the past. So it has been known for a long time that if you have 2 point lenses, a binary lens, then the total number of lensed images is equal to 5. And for 3 point lenses, it's 10, okay? So the sequence seems to be 5, 10, and what's the next going to be? Well, probably 15, right? Indeed, in 2001, Sun-Hong Rhee conjectured that the total number of lensed images for n point masses can be at most 5n minus 5. Well, compelling, right? Well, actually, Rhee was able to show sharpness of that inequality. So, in fact, she was able to construct a situation where 5n minus 5 gravitationally lensed images actually occur. And, well, this turns out to be a highly symmetric configuration. So you have to put n-1 equal point masses at the vertices of a regular polygon in the lens plane and a tiny perturbing mass at the center in order to achieve this. So physically, it's not particularly realistic, but anyway, this number can actually be attained, even though usually it will be less than that. Well, but how can we show the conjecture? And it turns out it's actually useful to complexify the problem. So complexify the lens plane and the source plane in the usual way. And then it turns out that the lens equation for the system of n point masses is given by this equation here. And well, this complex map is a rational harmonic function. And in 2005, Kevinson and Neumann proved the following theorem. So given a rational harmonic function R, this equation will have at most 5n minus 5 roots, where n is now the degree of the rational harmonic function. Okay, so seeing now that our lens equation is actually a special case, this theorem clearly establishes Rhee's conjecture. So the answer is indeed 5n minus 5. However, there's more. So Kevinson and Neumann, when they derived it, didn't actually know whether their inequality was sharp or not. So I should say these were pure mathematicians. They didn't have anything to do with gravitational lensing at this point at all. But then they discovered that Rhee had constructed an example which actually establishes sharpness. So indeed, this is a case of astronomy helping mathematics, as I said half jokingly at the beginning, right? And so at this point, I would like to welcome my students from 307 Complex Variables. Actually, today in class, we've started to talk about harmonic functions, right? So you can see that you can actually do some interesting research in this area as well. And I would encourage you to have a look at a beautiful article that Kevinson and Neumann in the notices of the American Mathematical Society, entitled "From the Fundamental Theorem of Algebra to Astrophysics, a Harmonious Path." Right? And if you're interested, the actual paper reference is also given here. All right, so so much for well, image counting. So far, we've been just looking at the integer number of lensed images that we can have. Now, what about final properties of the gravitational lensing map? So next, I would like to discuss gravitational lensing magnification. So here's again our lensing map, eta, from the lens plane to the source plane. And let's say it's differentiable locally. And then, of course, we can define the Jacobian in the usual way. And now from physics, it turns out that well, gravity doesn't change light intensity. Right? Classical gravity, classical general relativity, doesn't provide any absorption. There's no quantum stuff going on. So basically, gravity can only rearrange light rays, can only change the density of light rays. So therefore, the flux, which is energy per unit area per unit time, is proportional to the solid angle subtended by light bundle. And well, in the source plane, in the lens plane, we're using angular coordinates, so we can actually relate solid angle elements in the lens plane in the source plane. And of course, they're just related by the determinant of the Jacobian. And therefore, we can now define the unsigned magnification of a lensed image simply as the flux with and without lens, which will be the ratio of the solid angle elements. So it's 1 over the absolute value of the determinant of the Jacobian of the lensing map evaluated at an image. And well, there's also a sign, of course, and this is called image parity. So gravity can actually flip the orientation of an image as well. This will be the case at a saddle point, right? Okay, so now a regular lensed image is one for which the determinant of the Jacobian is non-zero, or physically speaking, if this was a gravitational lensed image, it has finite magnification. Now, what about singular images? So these will be images for which the determinant of the Jacobian is 0. In other words, where the image magnification would be infinite, at least formally. Of course, in reality, that doesn't really happen. And so the set of all these critical points in the lens plane is called, well, the critical set. One example that you might have heard about is Einstein rings. So if you have a perfectly symmetric, circularly symmetric configuration, you can have gravitational lensed images that are just circles. And these are bound to be critical images. Now, taking the critical set and mapping it back to the source plane with the lensing map, we get the caustics in gravitational lensing. And so caustics in the source plane. And caustics will be points or curves, and they will delimit domains of constant image number. So when the light source crosses a caustic, the number of gravitational lensed images can change. Well, it changes by 2, actually. And now, as you know, by singularity theory of Arnold and Thom, only certain types of caustics can occur generically. And in the gravitational lensing context, these are folds, cusps, and if you consider one parameter families of lens models, also higher singularities. So for example, umbilics and swallowtails. And well, we can now plot, for example, these higher singularities in parameter space, and then we get these characteristic shapes, right? So on the left, it's an elliptic umbilic, and on the right, a swallowtail. So for each horizontal slice of these boxes, each horizontal slice would be, let's say, a source plane. So you'd get a curve corresponding to a caustic in the source plane. Okay, so now I would like to discuss a particularly interesting property, well, I think it's particularly interesting, of gravitational lensing magnification, and that's magnification invariants. So what are magnification invariants? Now, it turns out, under certain conditions in gravitational lensing, the sum of the signed magnifications is equal to a constant. So even though, let's say, the image position changes, the magnifications change, maybe even the model parameters change, the sum of the signed magnifications is unchanged. And that's quite a curious property. So it doesn't always happen, only under certain conditions. And one particular example that I want to discuss here is called universal magnification invariance. So this happens when the light source is close to a caustic. And it refers to the images that are produced by this, called a caustic multiplet. So when the light source is close to the caustic in this maximum caustic domain, we get the property that the sum of the signed image magnifications, so magnification times parity, summed over all these images in the caustic multiplet, is equal to 0. And the nice thing about this property is that this is actually independent of the lens model, because caustics are generic, right, as we've just said. So this means locally, close to a caustic, all gravitational lensing maps will have a particular form. And then this means that we get these universal relationships here. Now, there's a fly in the ointment, though. So in practice, this doesn't seem to work as well. So here's another concrete example of a gravitational lens system. And I would just like to draw your attention to these images labeled A, B, C in the picture. So it can be shown that these images are created by the light source being close to a cusp caustic. And so by the theorem, we would expect that the sum of the signed magnifications should add up to 0, but it's not really the case. Now, why is this? We don't really know. I mean, the theory is correct, certainly. It probably has to do with you know, some complicated astrophysics, which I could go into, but of course, this is not the right place to do it. Anyway, so there's an interesting astronomical problem, and this has inspired a mathematical question. So what are these magnification invariants actually geometrically? And I think this is useful to ask, because that might tell us, you know, to what extent such magnification invariants are actually generic or not. Can we really expect them to hold under more general circumstances? And that would then, of course, pertain to actually applying them in real gravitational lensing situations, as we've seen. And well, so a long time ago, I suggested that we could actually do this by looking at Lefschetz's fixed point theory. Now, as you know, a function from a closed manifold into itself will have fixed points. And Lefschetz's fixed point theory then connects local properties at these fixed points, called the fixed point indices, with a more global property of f on this manifold M, called the Lefschetz number. So there's various forms, of course, of the Lefschetz formulae, but they're always of this form. So the Lefschetz number is equal to the sum of locally defined fixed point indices over the set of fixed points. And now, in particular, for complex manifolds, there's a holomorphic Lefschetz fixed point formula. Right? Now, it turns out, and I won't have time to go into lots of details here. It turns out that we can translate the gravitational lensing problem to a holomorphic map in such a way that its fixed points correspond exactly to the lensed images in this maximal caustic domain. And the reason this works is that, as I said, caustics are generic. So close to a caustic, they can actually be described by certain polynomial maps. And therefore, we can turn these polynomial maps into a holomorphic map. And moreover, it turns out that the holomorphic Lefschetz fixed point index defined for this function is actually exactly the signed image magnification in gravitational lensing. So can we now apply this in the Lefschetz fixed point formula? Well, not really, because this only works for closed manifolds. And of course, C2 is not, right? But one can use a trick. So one can homogenize and extend little f to another function from CP2 to CP2 in such a way that the restriction of this function to C2 is actually our original set of fixed points corresponding to the gravitationally lensed images. And then, of course, as always, CP2 can be understood as C2 together with, well, the infinity of C2, CP1. And now we're ready to actually apply the holomorphic Lefschetz fixed point formula as follows. So this is roughly the argument. It turns out the holomorphic Lefschetz number for f is 1, and then this is the formula here, right? And then we can break this down into the restriction on C2 and on infinity of C2, which is CP1. But of course, this mapping here on the right is again a mapping on complex projective space. So this actually again gives us this also sums to 1. And well, by construction, the restriction to C2 just translates to the sum of the signed image magnifications in gravitational lensing. So we see that this actually implies, indeed, the statement that we had, that the sum of the signed image magnifications taken over the caustic multiplet is equal to 0. So in other words, for these universal magnification variants, there is a, well, at least partially topological interpretation as well. Right, we call that the Lefschetz number is a homotopy invariant. So this shows that there is at least some topological information that goes into this as well. But this is just a simple example. Of course, the argument can be extended to other cases. There are other magnification invariants. So this is an example where the sum is equal to 0. The other ones that are known mysteriously are actually sums of image magnifications adding up to 1, 2, and 3. So there really seems to be something topologically going on, but it's not totally clear. So I think this is still an interesting little research area. Okay, so hopefully I managed to convince you that even in this physically rather simple standard approximation of gravitational lensing, there's some interesting geometry going on. But as I said at the beginning, of course, gravitational lensing is really taking place in space-time, right? So the real arena of gravitational lensing is Lorentzian geometry. So now in the second part of the talk, let me discuss some properties of the optical geometry. Now, a space-time, as you know, is a four-dimensional manifold with a Lorentzian metric. And here we are concerned with special spacetimes. First of all, a stationary spacetime, which has a time-like killing vector field. And well, this means then there's a chart in which the metric, or the line element, see if I can make this bigger, can be written in this form here. So this means the components of the metric are time independent, but there are some mixed time-space components. Now, if this vector field is also hypersurface orthogonal, then the space-time is static, and this means that the metric can actually be written in this form. So there's now no mixed time-space component anymore. All right. Now imagine taking Maxwell's theory of electromagnetism and studying it on such a Lorentzian spacetime, where then it can be shown that light rays, which is of course an electromagnetic phenomenon, is described geometrically as a null geodesic. So ds is then 0, and then we can solve for dt. And then by Fermat's principle again, we get a geometry in three-dimensional space such that the geodesics correspond to spatial light rays. And this is what we mean by optical geometry. So let's look at the static case first. Well, so here's our static space-time metric again. For ds equal to 0, solving for dt, you see we get this Riemannian metric on three-dimensional space. And again, by Fermat's principle, geodesics of this metric corresponds to spatial light rays. So therefore, this metric is called the optical metric of that static spacetime. Now, what about a stationary spacetime? Well, if we do the same, this is what we get, right? And well, this is not a Riemannian geometry at all. It's actually a Finsler geometry of Randers type, and I'll talk about this in more detail later. But the point is really this optical geometry is the proper well, differential geometry to study gravitational lensing. So remember earlier we were talking about this standard approximation by which a light ray is basically a straight line until it intersects the lens plane, and then it gets a kink, right? And of course, physically, this is not really what's going on. In reality, of course, the light ray will just be bent, and this bending is exactly what's being expressed by these optical metrics. So this is actually what we should do. So let's look at a simple example. In fact, let's consider a Schwarzschild black hole, which is static, spherically symmetric, and its optical geometry is Riemannian, and it can be written in this way. So what does this look like? Well, first of all, by spherical symmetry, we can, without loss of generality, of course, restrict ourselves to a plane through the origin, say the equatorial plane, and then to picture the optical geometry, we can embed this equatorial plane into three-dimensional Euclidean space. And doing this gives us this sort of funnel shape here. Okay, so again, by construction, geodesics on this surface will be spatial light rays. And well, you can see a particularly interesting radius here. So this corresponds to r is equal to 3m. This is the radius of the photon sphere, where we actually get spherical photon orbits encircling the black hole. Okay, now if you look at the surface, you notice immediately that the Gaussian curvature of the surface is actually negative everywhere. Why? Well, clearly, the principal curvatures have opposite sign, right? So of course we can also work it out. The Gaussian curvature is everywhere negative. Now, what does this mean for the light rays? What does that mean for the geodesics on that surface? Well, of course, by geodesic deviation, this means that light rays must actually diverge everywhere locally. Okay, but this is rather funny though, isn't it? Because we know that at the light source, light emerges, so it diverges there, but light then reconverges at the observer. And in fact, we can see multiple images of the same light source. So how is this possible? How can light reconverge at the observer if it actually must diverge everywhere locally on the surface. So it's a, well, it seems to be a little paradox. It's not. The reason, of course, is that this surface has a non-trivial topology. It has a hole. And it turns out we can use the Gauss-Bonnet theorem to exhibit nicely why this topological contribution is actually essential for the multiple images to occur. So here's the Gauss-Bonnet theorem. As you know, it connects local geometrical data like the Gaussian curvature and the geodesic curvature on the smooth parts of the boundary curve with the global topological property of that region, the Euler characteristic. And well, you might say, okay, Marcus, why didn't you just multiply through by 2 pi here? Actually, I want to write it in this way because these 4 factors of 1 over 2 pi are, of course, constant in Riemannian geometry, right? But actually turns out in Finslerian geometry, they are not. They will actually depend on position. So I mention this briefly again later, but the Riemannian version is, of course, as shown here. And I should also point out, of course, that the geodesic curvature vanishes for geodesics by definition, but that's particularly interesting for us because geodesics are by construction light rays, right? So this simplifies computations using Gauss-Bonnet a lot. So then how can we apply the Gauss-Bonnet theorem to study gravitational lensing? And so this is an approach I've developed with Gary Gibbons back in Cambridge a long time ago. And by now, of course, there are many applications of this in the literature. And in fact, at the moment, I'm working on a monograph with Ali Pettis, which will then also explain the state of the art of this optical geometry approach. But for now, let's just look at a couple of simple examples to give you an idea. So first of all, let's see how we can use Gauss-Bonnet to study image multiplicity. In other words, how many lensed images we can get. And to do this, so let us consider a light source S and an observer O connected by 2 light rays enclosing the gravitational lens L. Now, if this lens is a Schwarzschild lens, we've already seen that there will be a hole, right? So we could also have an inner boundary curve, and as the inner boundary curve, we take the radius of the photon sphere. Now, if the lens was just a regular galaxy, actually there would be no hole. It would just be regular. Right? There would be no hole. So we can consider the case of no holes or 1 hole. And then let me also note that all the boundary curves where they occur are geodesic, so the geodesic curvature vanishes. So now we can just apply Gauss-Bonnet and get this statement here. So the sum of the 2 angles between the light rays at the source and the observer equals 2 pi times the number of holes plus the integral of the Gaussian curvature over this region. Now, we've seen that for Schwarzschild, the Gaussian curvature is negative everywhere. However, for multiple images to occur, the left-hand side must be positive, right? We must have 2 positive angles. So you can see this can only possibly work if the number of holes is indeed 1. So in other words, the topological contribution here is really essential for multiple images to occur. So this is how we can show it for Schwarzschild, but of course you can easily imagine how to construct more complicated situations and how we can study image multiplicity in other cases as well. Now, let's see how we can use this method to actually work out how large the deflection would be. So here's again the picture, and now let's consider a different domain. So let's suppose we put the light source and the observer at some distance r, big R, from the lens. And then we take one of the 2 light rays as a boundary, and then we introduce another boundary, namely this circular arc of radius r, connecting the observer and the light source. So of course, then this gives us a topological disk, like so. And then we can let r go to infinity in order to determine the asymptotic light deflection angle. While doing this then, Gauss-Bonnet tells us that the light deflection angle is minus the integral of the Gaussian curvature of the optical metric integrated from the light ray outwards to infinity. And so that's a general result. And well, this is actually rather surprising because in lensing, you would expect that well, the strength of the lensing effect would be proportional to the mass enclosed within the impact parameter of the light ray. right? This formula actually tells us that we can get the same thing by integrating a quantity from the light ray outwards to infinity. We can look the other way, so to speak. And well, this is just to reiterate that gravitational lensing is a partially topological effect, right? So it has some global properties as well. And well, so there's lots of applications to all kinds of situations, so I won't go into them here. But let's just look at the Schwarzschild example, very simple. So let's suppose you wanted to work out the leading order light deflection angle. That's the sort of classical value that has actually been, observed by astronomers. Well, then what can we do? We can take an undeflected light ray as a sort of leading order approximation, plug it into the formula, and then find that the asymptotic light deflection angle is 4 times the mass parameter of the black hole divided by the impact parameter, which is of course exactly what we would expect. And then you can imagine grinding out higher order terms by successively approximating the actual deflected light ray. Okay, so this is the Gauss-Bonnet method. Let me now come to a different topic in the Riemannian optical geometry, and that's the isoperimetric problem. So first of all, in Euclidean space, as you know, we have the property that if an area is enclosed by a perimeter curve, then the length of that perimeter curve squared must be greater or equal to 4 pi times the area enclosed, right? And this is the isoperimetric inequality. And the limiting case where we have equality is, of course, the circle. So this is sometimes called the solution of the isoperimetric problem, in the sense that this is the perimeter minimizing length for a given area, right? And this is also referred to as Dido's theorem, because supposedly Dido, the Queen of Carthage, discovered this by trying to stake out the maximum possible area given just a short piece of string, right? Anyway, so the reason I'm bringing this up here is that I think the isoperimetric problem is actually interesting for gravitational lensing, because remember, in the optical geometry, length actually corresponds to light travel time, right? So therefore, if we have a general geometrical constraint on light travel time, this might actually tell us something about the time delay between images. And this is something that astronomers can observe. So remember, in the picture that we saw, or several pictures, we have multiple images of a quasar, let's say, but a quasar actually is a variable light source. And we can see this change in brightness with a time delay in all the lensed images. So the time scale is, days or maybe hundreds of days. But of course, the quasar might be located at a distance of, billions of years in light travel time. So therefore, a travel time difference of just a few days is a tiny, tiny fraction. So this could provide potentially, some very precise tests of a theoretical question that we might ask. So I think this is quite interesting. So anyway, a first step towards this is the following theorem. So this is work with Henry Rush at Columbia and currently in press. So this says, in equatorial Schwarzschild optical geometry, a curve of constant radius minimizes length within the homology class of piecewise smooth curves bounding, together with the radius of the photon sphere, the area between this constant radius and the photon sphere. And I'll come to a proof of this in a moment. However, we can immediately deduce a little corollary, which is applicable to gravitational lensing. And it's a kind of Dido theorem for lensing, right? And it says, in Schwarzschild optical geometries, it's light rays that bound solutions of the isoperimetric problem must be on the photon sphere. And why is this? Well, so curves that bound solutions of the isoperimetric problems are circles. Light rays are geodesics, but the only geodesics that are circular are on the photon sphere. So it's really like Dido's statement. Well, how can we prove the theorem? So there's a way to do this constructively. And this actually uses a trick that Hugh Bray at Duke introduced in the context of proving the Penrose inequality. Of course, different context, but we can use something similar here in optical geometry. So what we can do is we can rewrite the optical metric in different ways inside and outside of this radius r equal to c. and with some matching conditions. I won't go into the details, but the point is, inside of C, the metric is conformally related to another metric here, and we can define a reference, another reference metric by setting this conformal factor equal to 1. Now, if you do this, the following happens. So here's again a funnel of the Schwarzschild optical geometry. Inside of R is equal to C, in this HC metric, the optical geometry is actually turned into a cone. And of course, a cone is locally Euclidean. So we can translate our problem in the optical geometry to a problem in this conic surface. And for this, of course, we can use the Euclidean version of the isoperimetric inequality, and then we can translate back up to the optical geometry problem. So this is roughly how the proof goes. But so this is the limiting case. Now, what you might ask, okay, what about the actual isoperimetric inequality? Well, it turns out we can also show an isoperimetric inequality using a curve shortening flow. Now, curve shortening flow looks at a one-parameter family of closed curves that satisfy this differential equation here, where kappa is the geodesic curvature again, and n is the now inward-pointing unit normal. And then it can be shown here by topping that the length of the perimeter curve shrinks according to this integral here, and the area swept out by the shrinking closed curve obeys this integral. And this is actually a very powerful statement and allows us to show the following theorem. So let's suppose you have an annular region bounded by a closed curve C outside and gamma inside. And the Gaussian curvature is bounded from above by a negative number minus little k squared. Then we can show that the length of C squared must be greater or equal to the length of gamma squared plus k squared times the area enclosed squared. And so this is an isoperimetric inequality that would actually apply to gravitational lensing situation. Just recall that the Gaussian curvature in the Schwarzschild case is negative everywhere, right? And of course, any isolated lens, if you go sufficiently far away, would of course look like a Schwarzschild lens. So one of the things I'm doing at the moment is to think how this could be extended and actually applied to a situation that's interesting for gravitational lensing. Okay, so much for the Riemannian optical geometry. Let's now go to stationary space. Again, just to remind you, in a stationary space-time, we can write the metric in this form. So therefore, now solving for the optical geometry, this is what we get. And we get two parts. We get a part that is, again, Riemannian, but we also get a one form. And so this, of course, clearly cannot be a Riemannian metric. It's actually a Finsler metric. Now, what's a Finsler metric? Excuse me. So in Finsler geometry, we have a Finsler function f, which is a non-negative function on the tangent bundle, or well, I should say the slit tangent bundle, that is also homogeneous in the sense, well, homogeneous in the vectors, in this sense, and also convex in the sense that the Hessian of f squared with respect to the vectors is positive definite. Now, this Finslerian Hessian Gij looks rather like a metric, doesn't it? And in fact, one can use Euler's theorem of homogeneous functions to show that f squared is actually Gij times Vi Vj. So that certainly does look like a Riemannian length of a vector squared, right? But of course, the big difference is that unlike a metric, this Finslerian Hessian Gij depends not only on the point downstairs in the manifold, but actually on the vectors themselves. And of course, that makes all the difference. So one can introduce a tensor called the Cartan tensor, basically the derivative of this Finslerian Hessian with respect to the vectors, that kind of measures the deviation of this Finsler geometry from a Riemannian geometry. Right? This Cartan tensor would be 0, of course, for Riemannian geometry. So now, what would this look like concretely in general? Say we consider the Kerr solution. So the Kerr solution is the solution for rotating black hole. So in addition to a mass parameter, you also have an angular momentum parameter. There's this little a here. And well, I mean, I won't write out the line element in all its glory, but suffice it to say that we can find the optical geometry as discussed before. And here's the Riemannian metric, and here's the one form. And now by Fermat's principle, dt is now f x dx, right? So this would be a Finsler metric of Randers type. But of course, we have to make sure, just going back here, that this function f actually satisfies all the criteria. It has to be non-negative, homogeneous, and convex. You can kind of see from the definition here, it will certainly be homogeneous, but positivity on convexity are ensured by this condition here, as it turns out. So basically, the one form has to be sufficiently small relative to the Riemannian metric h. And so this just comes from the mathematics, of course, but what does this mean physically? And actually, it turns out, surprisingly, it has a nice physical interpretation. So this is what it translates to in terms of, well, the usual Kerr space-time properties, but it turns out to hold precisely outside the ergo region. And as you may know, the Kerr space-time has an ergo region inside of which an observer can no longer be static, so it's dragged along. And the outer boundary also coincides with the optical geometry ceasing to be a Randers metric. And so that it's like an optical interpretation of the ergo region. Okay, now earlier I mentioned this Gauss-Bonnet method. What can we do in a Finslerian or Kerr-Randers setting? So there's various things one can do. First of all, one might actually translate the problem into a well, fiducial Riemannian problem. And this is actually an ancient approach to Finsler geometry, which was developed by a Turkish mathematician called Nazim. Well, I should. It doesn't have a dot, I think. It's Nazim, who was a student of Hilbert. And so this is the early days of the study of Finsler geometry. And so he considered Finsler problems translated to Riemann problems by defining in a suitable way a vector field, which then turns, of course, the Finsler Hessian into some fiducial Riemannian metric. And well, this is what's called the osculating Riemannian geometry, and it's particularly useful if the geometry is only weakly Finslerian in a certain sense. So it actually works quite well in the case of a Kerr black hole where the rotation is comparatively weak. So one can construct this and then work out gravitational lensing, much like what we've done before, but now for the osculating Riemannian geometry. And now you get something slightly different. You actually get a direction-dependent deflection angle, which also depends on the angular momentum parameter of the black hole. And again, this can be extended to all kinds of exotic spacetimes that I'm not going to bore you with at this point. Now, there's another approach by a Japanese group. They say, well, we can, of course, do lensing in three-dimensional space. It doesn't have to be the optical geometry at all. That's, of course, perfectly fine. But that means that light rays are, of course, no longer geodesic. So we're certainly losing some properties there. And, well, that's one approach. But to my mind, the most elegant approach would be, and this hasn't actually been done yet, so it's kind of an open problem, is to do it intrinsically in Finsler geometry. And well, the hurdle is that Finsler geometry is not so easy, right? It turns out that there actually exists a suitable Gauss-Bonnet theorem in Finsler geometry, which was developed by these gentlemen here in the Kyoto Journal of Mathematics, 2010. And well, I won't go into it, but I think, as you can see, it's a lot more complicated. I'm trying to wrap my head around it. But one thing that I might point out here is these 1 over L's. L is the length of the indicatrix, is kind of the unit circle in Finsler geometry. And in Finsler geometry, this will then be position dependent. So this 1 over L then turns into 1 over 2 pi if you're in Riemannian geometry, and then we can recover the standard Gauss-Bonnet theorem. But anyway, so this kind of Gauss-Bonnet theorem might actually be useful to study the optical geometry of stationary spacetimes. Okay, so this is all for the optical geometry that I wanted to talk to you about. Now, all of this is actually within the framework of Einstein's theory of gravity, right? General relativity. And people are now also interested in modifying the theory, going beyond Einstein. And let me just spend a few minutes to give you an idea of the approach that I'm working on at the moment, because I think it might be interesting for some of you. So how do we modify the gravity theory? Well, usually people just take Einstein's theory, the so-called Einstein-Hilbert action, and stipulate some kind of modification, right? Literally by writing down a different action. But of course, this begs the question, how would you choose such an action? And I think a very important question is such a theory predictive? Because surely we can say that, whatever theory you want to talk about, a physical theory ought to be predictive because it should predict the future. Almost by definition, this is what physics should do, right? So we need to have a well-posed Cauchy problem. But by just modifying the Einstein-Hilbert action in some way, this may not be the case. So I think we need a different approach. And this is what the constructive gravity program is dedicated. So we try to derive gravity theories in such a way that the theory is predictive by construction. Now, and this then might work for really a general background, not even a metric background. So let's consider this. Take a step back and just consider a smooth manifold without any, particular structure initially. And now we introduce some tensor fields that we just call geometry. It doesn't have to be metric. And while we can only, of course, talk about this geometry field if somehow we can probe it. So we also need some other field that we can call matter. And in principle, they can have arbitrary order, tensor order. Now, space-time geometry would be probed by test matter, which means that we can make the inference of f as small as we like. So actually, this would have to be a linear field equation, linear in f. So then the most general PDE that would correspond to such a test matter field would look something like this, right? So you have a test matter field, which is linear, and then acting on this is some complicated general differential operator that will depend on the field G, which we call geometry. Now, from this PDE, we can read off the principal polynomial. And well, physically, this would correspond to the null momenta, the null covector cone. And then, as you know, for causality, the Cauchy problem ought to be well posed. So P would have to be hyperbolic principal polynomial. Now, actually, we also need the dual principal polynomial. So this would be not on the cotangent bundle, but on the tangent bundle. Be hyperbolic as well. Now, for metric geometry, of course, this is already the case, right? We can just pull an index to get the duality operation, to go from covectors to vectors. But in general, of course, we can't do that if you have a non-metric structure. So therefore, hyperbolicity of the dual principal polynomial P sharp is a separate condition. So requiring that this is also hyperbolic is something new, and together P and P sharp being hyperbolic defines bihyperbolicity. And this is the criterion that we can apply for predictive space-time kinematics in general. And of course, if you're in a Lorentzian metric geometry, of course, this is the same as in the usual sense. And now, bihyperbolicity turns out to be a fairly strong criterion, and it turns out you can then stipulate that bihyperbolicity has to apply throughout the space-time. And then this actually allows us to derive criteria for gravitational dynamics given bihyperbolic kinematics. And this is an old idea that goes back to the Wheeler school, Hodgman, Kukash, and Teitelbaum in the 70s. And from 2012 onwards, one of my colleagues, especially Frederick Schuller, managed to extend this to arbitrary tensorial backgrounds. So we can now actually study non-metric geometries, for example, area metrics. Area metrics measure not line elements, but area elements. They're fourth order tensor fields. So they will have quartic principal polynomials, well, which may or may not be bihyperbolic, right? Only those that are bihyperbolic, and then apply this constructive gravity approach to actually derive what a predictive, well, solution would be in a particular situation. So for example, we can work out what an area-metric Schwarzschild space-time would look like, at least perturbatively, and without guessing, right? So usually in modified gravity, we would just actually guess such a solution, but we don't have to do this if we insist on predictivity. And now we can study light propagation on this background, and there we can have qualitatively new effects that metric geometry doesn't have. So for example, because we have a quartic polynomial, right? So let's say a product of two cones, we can have an effect like birefringence. So light can travel along different cones. And this is not actually mysterious. This is, for example, how electromagnetism works in a crystal, right? As it's well known like this. It's Icelandic feldspar or whatever it is, right? You can see very nicely polarization dependent propagation along these different cones. And something like this could also be the case in space-time if it has an area-metric structure. But of course, this will have a strong impact on the kind of gravitational lensing that you can have. So we can actually use lensing to test such theories and constrain whether we can actually go away from Einstein's theory. And at the moment, of course, Einstein's theory reigns supreme. There's no evidence for deviations. Well, not clear evidence anyway. And one particularly interesting thing at the moment, of course, is gravitational waves, right? So a lot of the things that I've been saying today about light, in some sense, can also be applied to gravitational waves, which are also, well, traveling solutions, right? And in the geometrical optics approximation, they basically follow null geodesics as well. Okay, so let me now conclude. Hopefully I've convinced you that gravitational lensing is really at the interface of mathematics and, of course, theoretical physics and also observational astronomy. And well, from the physical side, we can probe the fundamental space-time of general relativity, but possibly also some interesting modifications that are just emerging. But really from a mathematical point of view, there are lots of applications of Riemannian geometry, Lorentzian geometry, Finslerian geometry, some topology, some algebraic geometry, some complex analysis, right? And well, finally, I should like to point out that this ancient connection between mathematics and astronomy certainly thrives in this area. And with this, I thank you for your attention. Thank you very much. Okay, let me come back to
Marcus.
Thank you.
Are there any questions? Or if you want to ask, just unmute and ask right away.
Hey, Marcus.
Hi.
Hey, I actually have a very kind of naive question because I know almost nothing about the geometry, but I'm pretty curious about what you mentioned, which is in the Finsler geometry, the Gauss-Bonnet will have this 2 pi is not a constant, right? Depends on position. But what I can imagine is this 2 pi is always on the left hand side, and but if this kind of curve is not some constant, then can you tell us a little bit more about how you can show this Gauss-Bonnet formula?
Oh, well, how to show it is actually complicated. I'm not sure I can do this immediately, but intuition. So I think you can start. So in the paper, they start from Poincaré-Hopf, and right. So this is topological. We just need to have a manifold and a vector field on the manifold. And of course, you have a topology. So this works without introducing any geometrical structure. So the starting point is Poincaré-Hopf, and then you can derive Gauss-Bonnet from Poincaré-Hopf, and that's what they do. And well, it's rather technical. I mean, I can't say it immediately, but one thing that's different is, if I remember correctly, so in Riemannian geometry, if you consider parallel transport of a tangent vector, the parallel transport of a normal vector field will be exactly the same, right? So in other words, the angle between tangent and normal will just always be parallel transported. But in Finsler geometry, this is actually not the case. So you can have different types of parallel transport, parallel and normal. So that also gives you different curvatures. So in this theorem, what enters is the normal geodesic curvature coming from the normal vector field, not the tangent vector field. So therefore, it's actually also an issue how you define the jump angles, right? In Gauss-Bonnet, it's actually very easy. If you define the jump angle at a vertex as, well, actually, I think I can use the whiteboard, right? So let's say you have a vertex here, then as you know, we can just parallelly transport the tangent vector, and then here at a vertex point, there's a jump angle, right? Now, in the Riemannian case, it doesn't matter whether you choose the tangent vector or whether you choose the normal vector. It will have the same jump angle, right? But in Finsler geometry, that won't be the case. So it also depends on how you define the angle. There's, again, various notions of how you can define angles in Finsler geometry. So, for example, one way of doing it, well, of course, in the Riemannian case, we can just say it's an arc on the unit circle. In Finsler geometry, the unit circle would be, something different. It's the indicatrix, and then we can define the angle by measuring the Finsler length along the indicatrix. And I think that's how they do it. That's called the Landsberg angle. So all of these things are quite different. And
yeah, I can see.
Anyway, so
thank you very much.
And then, right, okay.
No, I mean, it's very interesting. Yeah, I didn't know that where it can be such kind of very complicated. And just another very quick question. At the very end, you mentioned that you want the Cauchy problem to be well posed, right? What do you mean by well posed? Do you mean the existence and the uniqueness, right? Or do you need those kind of solution to be somehow, in some sense, stable so that you don't have those kind of inflation? Do you need this restriction on that?
So you want to have a unique solution that depends continuously on the initial conditions, right? That's
yeah. So you do have this continuous dependent. Okay, and you do have those kind of there is no inflation for the solution, right? Which means exactly, if you have small initial data, then you still have the small final time. Is that right?
Yeah, I think so. So it's the standard case like in metric geometry, except that in a metric geometry, you don't have to worry about the difference between vectors and covectors, really, right? We can just, relativity, there's the convention that you put the index up or down, right? We just pull indices all the time, up and down. And but of course, mathematically, it's a big difference between a vector and a covector, actually. And once you no longer have a metric geometry, like in this case, you really have to be careful about whether something is a vector or covector, whether you have the principal polynomial on the tangent bundle or the cotangent bundle, right? Can you actually find a duality operation between vector and covector? So therefore, hyperbolicity of the dual of the principal polynomial is a separate condition, which happens to be, so it's not separate in the case of metric geometry, but once you go away from metric geometry, it will be a separate criterion. That's why we have this bi-hyperbolicity. But other than that, it's the same. Yes.
Okay, yeah, thank you. Very nice talk.
Thank you.
Any other questions? I have one actually. You had this theorem about the fact that the number of images is always an odd number, right? And you said something like this is in gravitational lensing, but that seems to be much more general, right? Isn't that also true if you have glass lenses or something like this, or is there any difference? And if no, doesn't that mean that this fact is even something more fundamental? And because you said at the end, you can also use these lensing or to probe Einstein's equations. Maybe this effect is much general, right? Is it, or what's the situation?
Well, so as I've described the derivation using Morse theory, of course we do have some conditions on the lens. So it's not always an odd number. It has, it's an odd number for an isolated lens that's also, well, that has the property of a smooth deflection potential. In fact, I mean, even for, let me share the whiteboard again. In fact, even for the upper bound that I was discussing, right, the total number of images is at most 5n minus 5 for n point lenses. Well, I mean, you might say clearly this is not an odd number, right? Not necessarily, it's 5, 10, 15. So the odd number theorem doesn't apply in this case. And the reason is that a point lens doesn't have this regularity condition. So its deflection potential is not smooth. So even for a point lens, the odd number theorem doesn't actually apply. Or for example, if you have the Schwarzschild lens, just a single point lens, it always gives you 2 images, not an odd number. So it's really for, but it's actually for a realistic lens. You see, these point lenses are not particularly realistic, but really a realistic rotation lens would be sufficiently smooth, it would be isolated, and therefore for real galaxies, this kind of odd number theorem actually works. But for more contrived situations like these point lenses, it doesn't. And yeah, by the way, in practice, one of these images is always demagnified and close to the lens, so you couldn't actually see it. So in practice, it's actually more like an even number theorem, because you regularly tend to miss one of the images. But anyway.
Yeah, thank you very much. That makes it clear. Thanks.
Okay, thank you.
So thanks for this interesting talk. I think I have a follow-up question to Peter's question. So is there a way to kind of construct a model system, small-scale model system, to test the theory? So the reason behind is, you know that I'm doing random materials. If you want to the desert dune migration, you can do satellite imaging, but it takes a long time. So the idea there is to say that we construct a downsized image with all the dimensionless numbers that is more or less match to the real desert sand. Then you can have some kind of a small scale. Perhaps you can think about. I'm thinking about whether it's possible to have a small scale experiments that matches, since the theory is general, right? So general means that it should apply to different scales. Another question is more related to the second question is more related to gravitational lensing. I know that this recent progress in this, I don't know how to pronounce, LIGO project is actually detecting the gravitational wave, right?
Right.
So I'm thinking about, can we give us some background on that? So what is the level of experimental proof of the current theory, and what is the future in this direction? Thank you.
Sure, yes, thank you. Good question. So again, let me go to the whiteboard. So it's actually possible to construct gravitational lenses for the laboratory. So I mean, I've described how the optics works. You can actually, at least for simple lenses like a Schwarzschild lens, you can construct lenses. They look a little bit like this, so they're almost like logarithmic in profile, and then light rays coming in here will be deflected exactly in such a way as you would expect for a Schwarzschild gravitational lens. And in fact, when I was in Japan with some colleagues, we were working with a company in Tokyo to construct gravitational lenses like this through 3D printing for different lens models. So for Schwarzschild lens, this is a well-known example, but we're wondering, can you construct physical models of lenses for more complicated gravitational lensing situations? Now, as long as you have lenses like a Schwarzschild lens, for static spacetimes, this is actually fairly easy. So you can easily turn the Riemannian optical geometry into such a lens in the laboratory. But the problem really starts when you have a stationary spacetime and a Finslerian optical geometry. So for this, you would probably have to have some very exotic materials. And in fact, I've been thinking a little bit about how this could be done. So as you know, there are these metamaterials which have some amazing properties. And it could be that with a metamaterial, we could actually construct a gravitation lens model for a rotating black hole. And now, as for the other question about gravitational waves, so I'm actually affiliated with KAGRA, which is the Japanese gravitational wave theorists in Kamioka in Japan. And as you know, this is currently the only operating gravitational lens detector in Asia. But of course, there are big plans in China to construct both a gravitational wave detector on the ground and one in space. So this is similar to the European, or now again, it's jointly European-American. The Americans dropped out because of funding reasons and then came back in late, called LISA. And so apparently the Chinese, the Chinese gravitational wave detector in space and the European gravitational wave detector in space supposedly should be launched around a similar time, so maybe in 15 years or so. And as for the on-the-ground detectors, as you pointed out, we have 3 operating ones, one in America, LIGO, so it's 2 detectors, of course, and one in Europe, Virgo, and then this one in Japan, KAGRA. And the more detectors we have, the better, because they can constrain the direction from which a gravitational wave has actually come. But this is really, I think it's an amazing moment. It's like, I said this this morning to my students in class, this is like a Galileo moment, because 400 years ago, Galileo used a telescope for the first time to explore the electromagnetic sky, right? And only as of 2016, we can now detect gravitational waves. It's an entirely new window on the universe. There's no way of telling, you know, how much this will tell us. And so it's really, it's an amazing time for that. And yes, so one could now apply many of the things that I was saying to gravitational waves, and also study other properties. So waves, of course, have 2 polarizations, and so you can see this would be interesting if you have polarization-dependent light propagation, maybe in a modified theory of gravity, and so on. Lots of applications. And yeah, maybe I should also point out, you might have seen in the media very recently, there was a great discovery of another merger of black holes of surprisingly large mass. This was announced only a couple of days ago, and that was also jointly detected by these gravitational wave detectors. So there's still a lot of new information coming.
Thanks.
Okay. So yes, and if some of my students are still listening, hopefully, you know, I've convinced you that in this area, there's actually scope for some mathematically and also physically interesting problems that are tractable. So I think many of you will be thinking about signature work projects quite soon, well, next year at the latest, right? And so if you're interested, please get in touch.
So thanks again, Marcus, for this very nice and interesting talk. I see there are no further questions.
Okay, thanks. Thank you very much.
So thanks a lot, and see you all next Thursday. Bye-bye.
Okay, bye-bye.